Today we're covering 6-2 from your textbook, which is about drag force and terminal speed or terminal velocity. So whenever you have relative velocity movement of an object, like a ball through the air, a frisbee through the air, a swimmer through the water, that's a fluid and something solid, for example, then we say that that object is experiencing a drag force. Now, your book is giving this model of drag force, okay, with giving it is proportional to a drag coefficient, and then in this case, it's giving air as the fluid, so it's giving air density, cross-sectional area, so like, how much, what's the surface area of like the baseball or softball, let's say, and that matters, right? And then the velocity of or relative velocity between those two objects squared. But that is not, you are not going to need that formula in this class, okay? And the reason is because on the AP exam, they are going to, in any question they ask about drag force, they are going to give you the dependence of the force on the velocity. And they're just going to give you the function right in the test question. And it is just going to be probably a constant times either velocity, like just without the squared as a linear function of velocity, or a constant times the velocity squared, something like that. So you really are never going to use the equation from the book. You're just going to use the equation that they give you on the test. And we are going to do some more sophisticated analysis of this. We're going to come back to this once you've had more calculus experience in your math class. But conceptually, this is not hard to understand. When we say that this force depends on the velocity, you can still understand that this drag force is going to get bigger, okay, as the object is falling or going faster and faster. So in this case, like if you're talking about something that's in free fall, okay, not a baseball that's being thrown horizontally, like from the pitcher to the catcher. But here I'm talking about something that's just falling, okay? Then we would say that, beginning, start straight away, the drag force is not very large because the object is not falling very fast. And so because that drag force depends on velocity, its magnitude is not very large. Okay, but then eventually, because the ball, this looks like a tennis ball, because it keeps getting faster and faster, the magnitude of the drag force is increasing, and eventually, this falling object is going to reach a point where the drag force it matches that of gravity. Okay, it's never going to overpower gravity. Why not? Well, it just doesn't, it's gonna have a situation, okay, where this object is not going to fall any faster. Its acceleration will be 0, okay, and then that's what we call the terminal velocity or the terminal speed. And so, but it wouldn't make sense for it the tennis ball in the midst of its falling to suddenly start to accelerate upward like drag force win over gravity. Okay. Now, that does happen if, like, for instance, a skydiver is falling right out of the plane. They will speed up, speed up, speed up. And their their body shape might reach a terminal velocity. Then they open a parachute, their acceleration will be upward because they need to slow down. But that's because a change in their shape, or the drag force has drastically changed. And that's a good thing because we want them to slow down before they land. Okay. All right. Then let's do a few examples of some free body diagrams. So here I want to compare two things that have the same mass but different surface areas. So I have some post-it notes here. Okay, so if you have a flat sheet of paper and a crumpled sheet of paper, okay, well, which one do you think is going to hit, is going to hit first? Well, the crumpled one. That didn't take a physics class to know that. But let's explain why, okay? And so if we're looking at the flat sheet, oops, I'm going to have to pause so that I can exit the presentation mode. Hold on. Okay, so on the flat sheet and the crumpled sheet, let's draw their force of gravity as being the same because they have the same mass. Okay, and then on the flat sheet, it's going to have a greater drag force because it has a greater surface area. So, let's say they're kind of like halfway down, through their fall. Maybe this one has, a box and a half, I don't know, worth of drag force. You can call this D, you can call it FD. Okay. But the crumpled sheet has less drag force because it has less surface area. So, maybe this is much smaller. Okay. So then because the net force on this has an acceleration, the flat sheet is accelerating down. Okay. The crumpled sheet is as well. They both have an acceleration down. But this flat sheet is accelerating less than the crumpled sheet because the net force in the down direction is less. Okay, gravity is winning to a greater extent for the crumpled sheet. Okay, then let's look at this example. This is an example where the masses are different and the surface areas are the same, size and shape. This is a sort of odd situation, but if you had a ping pong ball, just normal, and then one that you somehow filled with water, and you dropped them off a skyscraper, and I guess I'm saying like imagine them at the same time, like midair. So now in this case, you would have the one, filled with water has more mass, and so its Fg is larger. The one filled with air is less massive, right? So then as they fall, maybe this one filled with water, it's experiencing a drag force of one box, and so is the air-filled one. Okay, but the water-filled one right now is accelerating downward. Gravity is still winning. At this moment of time, the one filled with air is no longer accelerating. Okay, does that mean it stopped? No, but it does mean it's got a constant velocity that's equal to the last velocity it had. That's why we're calling it the terminal velocity. So whatever velocity it had right when the drag force finally balanced with gravity, that's the velocity it has to keep for the rest of its fall. Okay. So maybe we'll do some Googling of terminal velocities of different objects. But that applies to, falling objects usually, I would say, versus objects that might be propelled through like a cannon or, you know, pitched sideways. That's a little different. Okay.